How do transfer functions work with Laplace transforms? Have you ever wondered how engineers analyze complex systems without getting lost in complicated equations? One of the key tools they use is the transfer function, especially when paired with Laplace transforms. So, how do these two concepts work together? Let's break it down in simple terms. Transfer functions are mathematical representations that describe how the output of a system relates to its input in the frequency domain. This means they help us understand how a system behaves when we apply different signals, like a sudden change or a continuous wave. The magic happens when we use Laplace transforms, which convert time domain equations into a form that is much easier to work with. When you start with a differential equation that models a system, applying the Laplace transform changes those derivatives and integrals into simpler multiplication and division by a variable called s. This transformation turns complex dynamic equations into algebraic equations, making analysis straightforward. To find the transfer function, you rearrange these algebraic equations to express the output over input ratio in terms of s. This ratio is what gives engineers insight into system behavior. The transfer function can reveal important characteristics of the system through its poles and zeros. Poles are values of s that make the function infinite, while zeros make it zero. Understanding poles is essential because they indicate system stability and how the system responds to changes over time. For example, in a resistor-capacitor circuit, the transfer function shows a single pole that helps us see how the circuit handles high frequencies and phase shifts. Using transfer functions with Laplace transforms allows engineers to analyze how circuits react to various inputs, like step or sinusoidal signals, without needing to solve the original differential equations directly. This method is fundamental in control systems and signal processing, where designing filters and controllers is crucial. In practical applications, transfer functions modeled through Laplace transforms support simulation and design tools like SPICE. These tools help predict and optimize frequency response, stability margins, and transient behavior efficiently. The representation in the Laplace domain also allows for graphical analysis on what is called the S-plane, which helps visualize system dynamics and design compensators. In essence, transfer functions work with Laplace transforms by transforming time domain equations into algebraic forms in S. This process simplifies the analysis of system behavior, stability, and frequency response, which are all vital in electrical engineering.